Hello, so in this video I'm going to be talking about nuclear chemistry. What we'll do in this video is go over some basic vocabulary, we'll go over different types of radioactive emissions, and then we'll show different nuclear reactions and equations that actually show these three main types. So before we do that, let's just go back a step and look at some basic understanding of atomic number and atomic mass and the number of electrons, protons and neutrons in an atom. So this is the notation that you often see to show an element that has mass number, or atomic mass number as it's sometimes called, certain number of neutrons and protons, and then an atomic number, which is Z, which is the number of electrons and the number of protons in an atom. So this is where it gets a little different for nuclear chemistry. So the general description of something like this, so an element that has certain number of electrons, certain number of protons, certain number of neutrons, we call it a nuclide. So a nuclide has almost identical definition as an atom, but it doesn't really specify the number of electrons. So a nuclide could be an atom or an ion. So an atom usually has equal, well it always has equal numbers of electrons and protons, so it's neutral. Nuclide could be an ion, so it could have a positive or a negative charge. Alright, so the other difference is instead of calling A, which is ordinarily the atomic mass number, we call it the nucleon number. So the nucleon number is the number of neutrons and protons. So almost identical definition. But the nucleon number, we used to call it the atomic mass number, but we'll call it nucleon number now. We're in the realm of nuclear chemistry, and it's the number of neutrons and protons. Also, each of these is called a nucleon. So neutrons and protons can also be described as nucleons. So it does get a little complex perhaps, but just to introduce that, but we'll practice it quite a lot, so it won't be too crazy. All right, so let's look at let's look at the ratio of neutrons to protons, and that's going to help us understand why some substances are just naturally radioactive. So smaller elements, or elements that have got a smaller number of electrons and protons. So for example, nitrogen, and oxygen's a good example. Carbon, a lot of the smaller numbers. Equal numbers of electrons and neutrons and protons, excuse me. So this ratio of neutrons is 1 to 1. So neutrons to protons, 1 to 1. And so I'm going to represent that on a graph. And imagine the green line has a slope of 1, right? So whatever number of protons you have an equal number of neutrons. So as elements get bigger, though, as the atoms, as you add more protons, you need more neutrons to keep the nucleus together, to act as the glue. And the more complex version is the quarks and the meson interaction, but we're not going to go there in this video. But just know that as the atom's nucleus increases in size, you need more neutrons to help maintain that nucleus. And so the ratio for larger elements, and bismuth is atomic number of 83, so it's got 83 protons in this nucleus, so you need 1.52 times that number of neutrons, so that'd be like 126, I believe. So you need a lot more neutrons to protons to act as that glue, excuse me, to keep the nucleus together. So the phrase for this, on a graph such as this, where we plot neutrons against protons and we're looking at stability, we call this a band of stability. So anything that's kind of above this or below it is unstable and therefore radioactive because it decays. So the nucleus isn't stable, so it breaks into a more stable arrangement, and that's what these three things are. So elements that aren't stable usually have high numbers, or a higher number of protons, usually, not always, and this ratio is a little higher, right? So for nitrogen it's 1 to 1, although there is radioactive carbon, which is 6 and 6, but or 1 to 1 again, but those instances are usually rare. Okay, so band of stability, so that's things that are on that red line are somewhat stable. Above it, unstable. Below it, unstable. And so what we'll talk about next is how an element can become more stable by undergoing one of these changes or one of these radioactive emissions. But the definition of radioactive is something that has an unstable nuclei, and we'll explore that a little bit more. But another way to look at it is where would it be on this graph? And if it's above the band or below the band, then the band of stability, then it's radioactive. All right, so let's just look at some more notation that gets used quite a lot in nuclear chemistry. Okay, so let's look at uranium, and this will actually be an example of a substance that undergoes alpha radiation or alpha decay. So uranium has the symbol U. You get that from the periodic table. You can also look up the number of, its mass number, or as we're calling it now, it's nucleon number. The atomic number doesn't change, that's still the same. But the difference is that this could be an ion. In nuclear chemistry, we don't necessarily represent it as an ion if it is. We usually just leave that off, and it's just part of the convention. So this could be an atom or an ion, but it's definitely a nucleon. Excuse me, nuclide. So uranium is unstable, and so the reaction that it undergoes, or the radioactive emission that it undergoes, is alpha radiation. Let me show that. But before I do that, actually, there's different ways to show elements that are nuclides like this. This would be one way. That would be another way, just missing off the atomic number. And then another way, which is a little bit more cumbersome, is the name and then the nucleon number. We'll be mainly using this one, but these are two other ways that you see radioactive materials represented. So, anyway, just going to erase that. But we'll be sticking to this notation. So this is an unstable nuclei, and if you just do the quick math in your head, if you do 238 minus 92, you get, a number that's bigger than 92. And so that means that where it would be on the band of stability on the graph that was here just a second ago, it'd be above the band of stability. So unstable, so undergoing alpha emission to become more stable. So, okay. All right, so uranium does this. So it reacts and it produces a more stable nuclide. So what happened here, the uranium is unstable. So to become more stable, its nucleus breaks apart slightly. And what actually happens is that it gives up 2 protons and 2 neutrons, so represented like this. So this is the mass number, or nucleon number, so 2 plus 2, 2 neutrons plus 2 protons is 4, and this represents the number of protons. In this case though, it does have a charge. 2 plus. So you often see alpha radiation described as a helium nuclei, and so a helium atom has 2 electrons, 2 protons, 2 neutrons. Helium nuclei just has the neutrons and protons, no electrons. Another way to describe it is a helium ion, right? So it lost those 2 electrons. But the idea here is that uranium is above the band of stability, so it's unstable, there's too many protons trying to exist in that small space. So it does something about it, and it undergoes alpha emission, and so it loses out of its nucleus 2 neutrons, 2 protons. So there's a new substance formed, and this is thorium. So you'll note here that the math, we went from 238 238 and 92. And then we went to, we can pretend that this is an equal sign. So the top row, if you just look at those values, and we'll ignore that 2 plus for now because it's going to get in the way. 238 equals 234 plus 4. Yes, it does. 92 equals 90 plus 2. Yes, it does. So conservation of matter and mass and energy all take a big role here because there isn't any electrons or protons or neutrons just magically disappearing. They're transforming, or they can be transformed, but in this case it's the most simple version of a radioactive emission. This nuclei is unstable, so it releases 2 neutrons, 2 protons, which is helium ion, and produces this new substance that's got a different number of neutrons and protons in its nuclei. So this is thorium. So uranium undergoes alpha radiation, and this is the Greek symbol for alpha. It's kind of like a fish, maybe. Maybe not. But that's sometimes how we represent it. And so this is the reaction that it undergoes. And this is how you can double check the math part. If you just look at the top row, everything should be equal. Conservation of matter, conservation of mass, and same on the bottom row. So 90, pretend that this is an equal sign. 92 equals 90 plus 2. 238 equals 234 plus 4. Alright, so it all adds up. Okay. So alpha radiation is the weakest, and it could probably just about pass through a piece of paper. So it's not the most dangerous, and you'd have to be pretty close to something that's emitting alpha radiation for it to really have any harmful effect on you. So it's the least dangerous. Still dangerous, but not as dangerous. Okay, so beta or beta if you're American, is represented with this B that's got like a longer line going off it. Same idea though, it's elements that are unstable, the radioactive, the unstable nuclei, they're above or below the band of stability on the graph, so there's got to be some kind of change for that element to become more stable, and it undergoes another different type of emission. A couple of different types for this one though. So this is the band of stability. The first example is one that's maybe above. And what that does is slightly different from what happens to an element that the ratio is too low. So this one has too many neutrons to protons. This one, an element down here, would have too few. So slightly different emission types. So the big, there's slightly different variations, but beta involves subatomic particles like a neutron or a proton changing. And so the first type would be a neutron, zero charge, becoming a proton and an electron. It's really easy to think here that a neutron is equal to a proton plus a neutron, because a neutron has no charge, and a proton and electron are negative and positive, so that kind of maybe makes sense. But that's not actually the case. It becomes a conversation about quarks, which we'll go into more detail in class if needed, but definitely don't think of this as one neutron is equal to a proton and an electron, just added together. That's not the case. So perhaps if that brings up more questions, we'll talk about that in class in a bit more detail. But for now, know that if we have an unstable nuclei, so in this case, let's look at iodine. So inside the nuclei of iodine, and not all iodine is radioactive, it's just a radioactive isotope. So, so we have this. So the neutron, or one neutron, splits into, or produces a proton and an electron. And so what that looks like for an element of iodine, or sorry, an atom of iodine, is that we get So in time it will become more apparent that if you see a problem or you're asked to determine or to write an equation for beta emission for an atom of radioactive iodine, then you'll gradually come to know that it means an electron. But in this case, one atom of iodine, inside the nucleus of this iodine, you've got one neutron splitting into a proton and a neutron. So in this case, the atomic number, which is 52 for xenon, actually goes down by 1 because it lost one electron. No change in the nucleon number, or the mass number, because electrons don't contribute to the mass, so this is 0. So if we were to do the math again, 131 equals 131 plus 0, yes it does. 53 equals 52 minus 1, again. Wait, that's not right. Yeah, this makes more sense. So 53 is equal to 54 minus 1. Yes, it does. Alright. So you're probably, in your head, you're probably thinking, well, Mr. Slate doesn't know how to add and subtract. But also, you're probably thinking, well, if this happened, doesn't this thing have a positive charge? Because an electron's given out, so there's got to be a proton left over, and that's absolutely true. So yes, it does have a positive charge because it did end up with one extra proton. It gained a proton, but because it's a nuclide, sorry, we don't tend to write that positive charge. So it is correct that it's an ion, but we don't represent it that way. Okay. So beta emission, in this example, if an element is above the band of stability, an electron is given out. So there's another version that we should go through. I'll leave that up. And this case, it's an element that's below. So the number of neutrons, the ratio of neutrons to protons isn't high enough, so it's still radioactive, but there's a different ratio than an element up here. So in this case, we can look at an electron. Oh, sorry, excuse me. So in this case, a proton splits into a neutron, and something called an antimatter electron, or a positron. And again, we're not going to go into too much detail on this in this video, but there are, again, it becomes this conversation about quarks, which is perhaps not what where we want to go with a brand new topic. But a proton decays into a neutron and not an electron, but think of a positively charged electron or an antimatter electron. Positron is the official name for it. So to see a reaction that involves that, we look at potassium. So an element of potassium, which is radioactive, and that undergoes beta decay to form argon plus this positron. So almost a similar idea, it's just that the signs are changed. So here you've got a radioactive isotope of potassium, so it undergoes decay, creates another neutron, and then wait. It's been a long day. So in this case, potassium decays into, so the atomic number goes down by 1 because that proton disappeared, and the atomic number doesn't take into account the number of neutrons. So then, in this case, we've got potassium decaying into argon, which is more stable, and releasing a positron, a positively charged electron. So, very similar to this, but this is an example of an element that's down here in the band of stability. Maybe not that low, but maybe lower than this example. Okay, so the last type that we're going to look at is before we get to gamma, there's another. No, let's go straight to gamma. Okay. I'm actually going to erase this so we've got more room. So before I do that, beta radiation or beta emission is probably can penetrate through a big piece of wood, so maybe a tabletop. But gamma radiation could probably penetrate through a wall. All right, so you need a really thick amount of concrete. Actually, lead does absorb gamma radiation really well. Those are the big heavy aprons that you wear when you go to the dentist. So they absorb gamma radiation. Beta, it kind of becomes increasingly more penetrative as you go this way. So alpha could probably get through a piece of paper. Beta, maybe a tabletop. And gamma could easily just zip right through a human body. So the example of gamma. So we're going to look at cobalt, which has this. So this is an isotope of radioactive cobalt. So it undergoes two different types before it gets, well, one of them is gamma, one of them is beta. So it undergoes beta radiation first, beta emission. So that creates an electron. So similar to this, obviously. And then it changes the nuclei, so we get nickel, which is 28. So this thing happens, a neutron becomes a proton and an electron. So we get a new substance, nickel, and the electron. So then there's another type of radiation emitted, and in this case it's gamma radiation. So it doesn't really involve any change, so we still get nickel, but we get this gamma radiation emitted, which is a stream of high energy photons. So photons are light particles, and so this nickel is in a really high energy state. And so as it stabilizes, as the electrons, which are all in higher energy levels, as they drop, this large amount of energy, or gamma radiation, is emitted. So it undergoes beta radiation first, or beta emission, excuse me. So it kicks out an electron, and then this nickel version of nickel is highly, highly excited. All the electrons are all in higher energy levels. So then as they eventually drop back down, because they can't exist in those high energy levels, then gamma photons are emitted. So gamma is very, very dangerous, very difficult to stop, because it's photons, light particles. Okay, so in the next video we'll talk about a bit more about nuclear chemistry and about how, at what rate some substances decay. The big idea here is that the three main types of radiation emitted, and this happens because elements are unstable. So it could be a radioactive substance, like all uranium is radioactive. Iodine, not all iodine is radioactive, but some isotopes are. Same with cobalt. So to become more stable, there's a change in the nucleus, and that can take on different forms. It could be losing an electron. It could be forming a positron. So slightly different versions of nuclear emission.